Is the corrosion testing, and what you see here on this slide are the two pictures showing the two different ways of corrosion testing of material, which is very important because we have to do the testing to qualify a material for the real-time application, and there are many other purposes for corrosion testing as you are going to learn in today's lecture. So the basic agenda of this corrosion testing is why we do that and what are the important criteria for the corrosion testing, how we can classify broadly the types of corrosion testing, what are the accelerated testing methods and why they are required for certain applications, which include dispersed fog spray method, high humidity, simulated atmosphere and the immersion in liquid, and then the general test to assess the corrosion damage. That includes the weight change test and the dimensional change test. The dimensional change, as you can see, can be done using the ultrasonic method, eddy current method, and the microscopic methods. And then you will also learn that there are certain tests which are specific to the types of corrosion. Finally, you will see a case study of how we choose the corrosion testing methods depending on the application, and a simple flow chart for the corrosion failure analysis, which is currently and mostly adopted by many consultancy organizations. So let's start with the corrosion testing. Four important points why we want to do the corrosion testing. The first is a material selection for a typical application. For any given application, you have to understand what is the atmosphere, and you have to choose the material which is most compatible with that kind of atmospheric condition. For example, when you use a material in the marine atmosphere, you may need a different material. When you want to use a material in the dry condition, it can be a different material. And if you recall that if you have the sulfur containing gases, you don't want to choose nickel. But if it's a halide attack, nickel is no problem. So this all material selection. So whenever we come out with a new material also, we have to qualify this material for engineering application, not only based on the properties like electrical or mechanical properties, but also from the corrosion perspective also. The properties, mechanical properties can be good, but if the corrosion properties are not good, that material will not succeed in the real-time application. The second reason why we want to do the corrosion testing is to develop the new corrosion preventing agents. Now, one of the corrosion prevention method is you can use the inhibitors, anodic type or cathodic type, or you can coat your material by paints. And you know that coating can be metallic type, non-metallic type, rubber type, and so many different types of coating, so many different type of inhibitors. People can market whatever they want to, but how do we know that this particular inhibitor is good for a particular application and for a particular material and for a particular environment? And that can be established when we carry out some level of testing. Quality control of materials and the protective agents. A typical example of a part used in the aerospace industry was found to corrode in the welded zone here. You see here is a part welded and you see the brown zone here. So this is typically the intergranular corrosion. While we are not supposed to see that in aerospace parts because they choose the steel very carefully. So people were surprised that why this material is still corroding after welding. So essentially they realized after testing that this material is not the one which was specified, but the supplier gave some other kind of material. So it's very important for the quality control. And once again, the research and development, you need the corrosion testing, qualification of any new material, or if you want to understand the corrosion mechanism, then you need to do the corrosion testing to establish that. So these are the four different prime reasons why the corrosion testing is being done by the people. Now, when we do the corrosion testing or when we come out with the corrosion testing, we have to ensure 2 points: that it is reproducible. That means if you want to repeat it 10 times, our results will be within a given scatter, which is not more than typically 5%, and it should be reliable. That means if we are trying to assess pitting corrosion by a testing method, the testing method should be able to tell the pitting susceptibility of a material. So it has to be a reliable method. We can do the corrosion testing either in the lab or we can do actually in the field test. So these two methods are used for two different purposes. When we do the lab testing, for example, our main intention is that you have 5 different type of material that you can use for an engineering application based on the properties. So you want to disqualify the material that are definitely not good. So that's where you do the lab testing. And when we do the lab testing, we just use a small samples, small volume of the liquid or environment. We use a simulated condition, and normally we go for the short-term testing. So once you get the results, you just try to disqualify the material and choose the one which are doing like exceptionally well, and then you take them to the next level. The point of caution is that we should not use the lab testing results to build up the industry level plants. So it is only for the lab purpose. When you really want to use your data for establishing new industries and so on and so forth, you must try to go for actual service condition. When we say actual service condition, that means your material has to be actual raw materials, actual concentration, actual volumes, and it can be short-term or long-term. So essentially, we do not simulate the condition. We subject them to the exactly the same situation as they will experience once that particular industry is performing. Now, example of field tests are shown here. For example, if you want to study the effect of atmosphere, we know that the corrosion rate will be different in rural atmosphere, it will be different in industrial atmosphere and marine atmosphere. Similarly, if you are trying to study the effect of soil on the corrosion susceptibility of the underground pipes and so many things which are underground, then you want to see what kind of soil you are dealing with. Is it a dry soil, it's a moist soil, it's a sandy soil, or it's a clay type soil. So all these soils will show the different kind of corrosion behavior for the same material. Similarly, water. Are you talking of fresh water, salt water, stagnant water, or the flowing water? If you are fresh water, for example, stainless steel will work, simple stainless steel. But if it's a salt water, that simple 304 and 316 steel will not work. Then you need molybdenum containing steels. Similarly, when you have stagnant water, again your stainless steel will not work because there will be a lot of pitting in there, like in the marine industry. But if it is flowing beyond 3 feet per second, you can still use them. So the material selection depends because the rate of corrosion will be different under different conditions. So essentially, people use the coupons, and here are some pictures which shows that the coupons are put on the racks there, and this location is in North Carolina, and this is again in the Harbor Island at North Carolina. The idea is to expose the sample to certain atmospheric condition and make a record. Here are some more pictures by the Defense Research Establishment here, and this is by NASA. So essentially what they do is that they put the coupons, and all the coupons are labeled, and this guy will come practically every week or every day and see how these samples are responding to the atmospheric condition. And he makes a note, and that establishes the corrosion behavior under a given atmospheric condition. Now, if you do these coupons and you expose them, of course you can do the long-term tests like 5-year test, 10 years test, 15-year test, but at times they are not practical because you know that every 6 months you have a different phone model, every 1 year you have a different car model. So the technology is changing very fast. We cannot afford to wait for a long time to understand the corrosion behavior. So what people do is that they come out with some accelerated method in which they run the corrosion test for a short period of time, extrapolate the data, and then come out with long range prediction, which normally are reasonably accurate but may not be accurate. So that chance you have to take. So there are 4 types of accelerated testing methods, and these are like fog spray method, high humidity method, simulated atmosphere method, and the immersion method. So in the first method, for example, in the dispersed fog spray method, what people do is that they it can be of different types, like and the types can be because of the way you spray the solution into an atmosphere, what kind of temperature you want to use, and what kind of composition of liquid you want to use. So there are many spray methods, but as I say here, the fundamental principles are all the same. And what are the fundamental principles? You take a coupon. You can take a painted coupons or coated coupons or passivated coupon. You scratch the surface. You incline at certain angle, 15, 30, 45, based on a standard. ASTM stands for American Society of Testing of Materials. And then you spray the chamber, and the spray should not fall on the samples directly. So these are the fundamental principles, irrespective of the type of the spray testing method you use. And this method is used to see whether the surface protection methods like paints and anodic films are working properly or not. So it is just to evaluate the reliability of the paints and anodic films. Similarly, you have the humidity test, and you know that humidity makes a major role. It differentiates between the dry type of corrosion and the wet type of corrosion. And we know that the gray area is around 60 to 65% level of humidity. So essentially, humidity tests are used not only to assess the protective coatings, but also about the sensitivity of the different materials towards the humidity. And also, you can study the effect of temperature. In planet Earth, you can reach up to 50, 52 degrees centigrade in certain location. So that is the temperature variation you can expect. And you also have the humidity chambers, tailor-made, which can be used to do this kind of testing. And once again, when you do any kind of testing, whether it's a corrosion testing, mechanical testing, any other kind of testing, try to look for standards. Because once you follow the standards, your results are acceptable at the international level. So essentially, for example, for the humidity test, you have ASTM standard here, written here, and another ASTM standard written here. So just follow whatever suits your requirement better. And the different level of humidity can be managed by using the different type of acid solution or the salt solution. So this kind of information is available. So this is only for your reference. Similarly, you have the simulated atmospheric test, and in that, at time, your application can be very complicated. You can have certain temperature, certain atmospheric conditions, certain amount of particles in there. So if you have not like a natural atmospheric condition, then you can create those situations in a tailor-made chamber like that. You have a weighing balance here. You hang the sample into this chamber and give all kind of condition in this chamber. And then you just measure the weight gain or weight loss, plug into the equation of the mils per year, and you will find the corrosion rate. Here is a picture of the people who wanted to study the corrosion of copper in deionized water solution because of the type of application they were looking for. So they created their own setup. They get the deionized water, they maintain the temperature, they maintain all kind of thing what they want to do, and study the rate of corrosion under the condition for copper. So these examples are plenty. Then you have immersion test. You know that offshore oil and gas refineries, many of the things are completely immersed. Some kind of offshore platforms which are partially immersed. And marine industry, part of the ship is above the water. So you have all kind of immersion situation, total immersion, alternate immersion, partial immersion, and that can be understood from this simple beaker with a coupon, metallic coupon here. So this area is subjected to the total immersion. This is at the water and air interface, and this is a air zone. So now the water can always evaporate and condense on this area. So the type of corrosion that this part is going to see is different from what it's going to see when it is in the completely immersed situation. And that will be different from what it sees at the interface. So you can just study 3 different type of corrosion situations here. So that kind of thing is very important for oil and gas industry, as I said, marine industry, and all kind of offshore platforms. These are the some of the standards which you do not have to remember. It is only for your reference, which are used for like understanding the water resistance of the coating, as in number 1, painted parts and panels. Number 3 is for painted parts. Number 4 is for sodium chloride solution, and number 5 is for resistance to liquid, immersion in liquids other than water. So basically, for different kind of situation, you will have the different standards. So that is where you have to see which standard suits your requirement, and you have to choose that. Now after that, the different type of accelerated test, we know that there are 2 ways in which we monitor the damage. And this damage monitoring is by the weight change test, which you have seen in the first lecture. Mils per year is equal to something into weight loss by DAT. And second one is a dimensional change test. In the dimensional change test, you can use 3 methods: ultrasonic method, eddy current method, and the microscopic measurements. So weight change test is just like, it's a very simple thing. What you need is an electronic balance, which will cost you just like $1,000 to $2,000. Very versatile. It can be used for most of the material, very cost effective, and can be used practically anywhere. So what you have to do is that take a piece of material, expose it to certain atmospheric condition, and find the weight loss or weight gain, and plug into this equation for the mils per year, and you get the rate of corrosion. Some of the cautions: you cannot just use any balance, use the electronic balance so that you can monitor the weight change in milligrams. You have to use the density from the handbooks, and you have to ensure that the dimension measurement are within plus minus 1%. So you have to use something like screw gauges and vernier caliper to be as precise as possible. And then you can get the value and get the corrosion rate. The dimension change tests are very important. For example, for the pipes, you want to know how the pipe wall has thinned down. Boilers, you again want to know the thickness of the wall, whether it's going to get overstressed and fail. So all those kind of application, you need the dimensional change. And for dimensional change, you can use ultrasonic method, eddy current method, and the microscopic method. Method number 1, ultrasonic method, is the most practical and feasible to do. Eddy current is also applicable, but with some limitation, and this is only for very special application, the microscopic measurement. So ultrasonic measurement can give you an accuracy of about 0.01 inch in its measurement, and it uses ultrasonic waves to find the thickness of the wall. And apparently, if you have the initial thickness and the thickness measured after a certain period of time, then you can get the change in thickness divided by interval time, and you can get how fast your wall is thinning. And you know exactly how much you are allowed to go in, and then you can always stop the operation when it comes to near to the critical level. Now, the change in the wall thickness or the rate of corrosion can change as a factor of many things. This is a hypothetical curve which shows the change in the thickness as a function of time. You're starting a chemical plant, and when the plant starts up, people normally find the change in thickness is more because the system is getting stabilized for a given atmospheric conditions. And then once it's stabilized, it will stay like that. But if you change any process parameters such as temperature, which always increase the rate of corrosion, again the change in the thickness will take place. And if you stabilize at that, it will come to a stable level. So there are many parameters. Change in the concentration of the solution that your material is handling, that can also change the thickness. So it's very important that the change in the thickness is monitored with time in the chemical industry, in the pipelines, in the boilers, and anything which is hollow. So here are the example, pressure vessels, pipelines, and all this thing. And the second method we use to find the thickness of the wall is the eddy current test. And as I indicated that it has certain limitation, it's only used for the material that conduct electricity. For the non-ferromagnetic material, can be used in the service condition. You have the standard equipment there, and you can get an accuracy of plus minus 2% using this method. And how does this work? Is based on the classical principles of physics. What you see here is the standard gadget that you can get for the eddy current testing. You need to calibrate your system, and it not only find the thickness, but it can find the hardness, it can find the compositional difference of the material. It has multi-purposes. How it works? You take a coil, you pass the AC current in that, it will generate a magnetic field, bring it to the specimen, near to the specimen. This magnetic field will generate the eddy currents in the sample, and that eddy current will generate its own magnetic field, which will be converted into a voltage signal, and that voltage signal is compared with the standard signal or the standard thickness or standard hardness or standard chemical composition, and you know exactly where the variation is, and you can quantify that. So that is the fundamental principles of eddy current testing. Used in many applications, but for thickness measurement of the wall, I think ultrasonic method is more popular than this method. Then you have microscopic measurement applicable only for situations where you can take a bit of sample, you can cut a sample out and examine it. So once you take a sample out, you just polish it, you see it in the microscope, and once you see in the microscope, suppose it has a cylindrical cross section, you see the original size here, and this is the final size where you have actually good sample, metallic sample, covered with the oxide layer here. So from outside you will see the final dimension as the one which includes the oxide layer, but in the microscope you will see which is the useful remaining part. So that happens only when you have the high temperature exposure. So people do it when they can afford to cut the sample out. Otherwise this method is not very practical. We also have the corrosion type specific test, and these tests are specific to the type of corrosion, and you have many tests under ASTM and NACE, National Association of Corrosion Engineers, and you also have the military standards by abbreviation of MIL, M-I-L. So there are these tests, plus there may be some other tests depending on the country you are in, and you can follow that. Now pitting, you know, is a localized type of corrosion. It can be very dangerous. It can be shown on the surface as some kind of fine, nearly circular circles kind of thing. So you can take the picture and you can compare with the given chart, and once you have this chart and you compare it, you exactly get the rating, and from the rating you will know exactly what is the cross-sectional area of the pit and what is the depth of the pit. I'll show that another chart a bit later on. So from just by comparing the photos, you can get how bad is the damage because of the pitting corrosion. Now you know the intergranular corrosion, where the corrosion takes place along the grain boundaries, typically shown by the stainless steel after the welding. That is called as intergranular corrosion. We learned that under the types of corrosion. So that happens when your steel is, for example, exposed to a temperature between 425 to 760 degrees centigrade, and the chromium carbide precipitates, and you have a chromium depleted area along the grain boundaries, and not depleted area away from the grain boundaries. So corrosion takes place along the grain boundaries. And this precipitation of chromium carbide is known as the sensitization. So once again, welding is a key factor, and the second factor is when people try to do the heat treatment to alter the mechanical properties of the material. So two reasons. Here's the picture. You have carbide here, and you have a depleted zone in chromium and carbon, and this area becomes anode, and the corrosion happens along the grain boundaries. Now, if you look at the literature, you will see that there are a lot of tests which are there to see whether your material is really sensitized. That means the chromium carbide has come out or not. So you have the first test, electrochemical potentiokinetic reactivation method, or EPR method here. Its limitation is that it saturates at high degree of sensitization. That means if your precipitation is really bad, it will not differentiate at the high level. Then you have ASTM A262A oxalic acid etch test. Again, it has the same limitation. It saturates at high degree of sensitization. Then you have ASTM A262B ferric sulfate sulfuric acid test. It may work on austenitic steel, but it does not work on the martensitic steel. Then you have again A262C nitric acid test. Again, it has a limitation of that it cannot work on the martensitic steel. And then you have 262D nitric acid hydrofluoric acid test. It may not work when the samples are limited in number. That means you need to have a good number of samples. So it is not very practical for using this test in the lab condition where we are always limited in samples. Then you have the Strauss test number F here, and it has the advantage that it does not saturate at high degree of sensitization, and you can work with a limited number of samples. And then you have number G, 262F, copper sulfate sulfuric acid test. Once again, it cannot work on the martensitic steel. So this was a problem came from the industry when they were using the martensitic steels. And these tests are all tailored for austenitic steels. So apparently it was modified for martensitic steels, and a new solution was created, and it was etched to reveal this, whether there are precipitates at the grain boundary or not. Now here are the three pictures here, top to bottom, which is not easy for every one of you to understand, but unless you are really sitting on the microscope, but these pictures you can easily understand. This is a section where your sample is polished, so it will look like a mirror, bright white surface. Now if you expose that to a solution, the solution will corrode the surface uniformly. If it is doing that, that means there is no precipitation of the grain boundary precipitates which lead to the intergranular corrosion. Now, if you expose a sample, and what you see here is still a shiny surface, but you see some kind of dark spots on the grain boundary. So you see here, you can see some dark spots along the grain boundary. Then this means that the precipitation has taken place, and this material may be subjected to the intergranular corrosion. If the situation is very bad, that means your precipitate not only comes at grain boundary, but it also comes within the grain. That means your chromium is totally depleted, and your material is going to corrode in a very severe way. So we call this as a heavily sensitized sample. So all this work was done in the lab only. So we give the rating, number 1, 2, 3, and 3 prime. Number 1, we cannot detect the sensitization. The attack is uniform. Number 2, slightly sensitized, some precipitates at the grain boundary. Number 3, very badly sensitized, but limited to the grain boundary, and severely sensitized, where you have precipitates not only at the grain boundary, but also in the grains. That means your chromium is not available to give a protective layer. Then you can create a graph like that, where you have y-axis, you have temperature, and x-axis, you have time, and then you have a shaded area here, which shows 3 prime. 3 prime is severely sensitized, very bad situation. So you can always choose your welding parameters or the heat treatment parameters to keep the temperature and time combination so that you are in 1 or 2 zone but not in 3 or 3 prime zone. So this is how the calibration charts are made with respect to a given material. So now this slide just shows you that how many different types of standards are there and how specific or general they can be. It's just for your example, you're not supposed to memorize any of it. First arrow shows the control of external corrosion on underground or submerged metallic piping system. So you have a test for that. If you look at the bottom one, you see the control of corrosion on steel, fixed offshore platforms associated with petroleum production. So it's very specific to platforms and the petroleum, not for any other system. Then you see here testing of metals for resistance to sulfide stress corrosion cracking. And this is again true for the oil and gas thing, because in some of the oil and gas wells you have sulfuric acid or H2S, not sulfuric acid, H2S, which can of course combine with water to make sulfuric acid. Then you have B117 for the salt spray testing, which is a general method. And if you just look below that, acetic acid salt spray fog testing. So you see that these two methods are already different, but both of them are the fog spray method. And if you look G34 at the bottom, you will see that it is the one for exfoliation corrosion in 7000 series alloys, which is a wrought aluminum alloys used in the defense applications. Similarly, you will see on the top is the recommended practice of determining the susceptibility of stainless steel and nickel chromium iron alloys to stress corrosion cracking in polythionic acid. So it's specific to the polythionic acids. And then you have recommended practice for conducting atmospheric corrosion tests of metals. It's a very general type of test which you can use for practically any kind of metal. So these are some of the examples. Now, how do we choose the corrosion testing methods? You have so many options: ASTM standards, NACE standards, MIL standards, and so on and so forth. So everything comes with some kind of literature search that you need to do, and it's not very straightforward. For example, I'll give you one case study when an oil and gas industry came to us, and their question was, they were using martensitic stainless steel here, and they want to see that how we can ensure that this will not corrode in their given atmospheric condition, which is the oil production. So we asked for the service condition, and they say it is sliding against each other, and they say that that type of environment is a crude oil and marine environment. So the request made is that what is the corrosion behavior of MSS in this constitution, martensitic stainless steel, and what lab testing should they use to ensure that they do not fail prematurely, because every day of operation shutdown may cost them millions of dollars, so they don't want to stop the production. So essentially, literature search was done to see that how the martensitic stainless steel fails, and we realized that it can fail by stress corrosion cracking, it can fail by pitting, can fail by corrosion fatigue, erosion corrosion, and cavitation erosion. So we are not talking of the highly turbulent fluids here, so this was ruled out. We are not talking of the stresses on this part, so this is ruled out. We are not talking of the repeated interaction of the metal or cyclic loading. This was ruled out, and we asked them whether there is solid particles in there, and they said no. So erosion corrosion is ruled out. So it was a continuous interaction between the industry and us. So you're saying that these are the possible ways, then based on that we asked them the question, they gave us the answer, and we narrowed down to the pitting corrosion. So apparently once we narrow down based on the continual interaction between us and them, then we look for the corrosion testing methods for the pitting. And when we go for that, now we see these kind of standards here. You have G44, which is for 3.5% sodium chloride solution, and the main intention here is for the alloy development. Then you have the B117 salt spray fog testing that only analyze the surface protection method. Again, modified salt spray for surface protection methods, and copper accelerated acetic acid salt spray testing again for the decorative coating. So obviously we are not talking about the coatings here, we are talking about the bulk material. So once again these three are ruled out. So G44 was the one which was chosen. We got the samples, and this includes immersion of the material in iron chloride solution for 3 hours, take the mass loss or the weight loss, and take the pictures and find the pit density. Similarly, because the oil and gas can also have the sulfur, so you go for the sulfate containing environment and you immerse that in the sodium sulfate now, again get the mass loss, take the value, put for the mils per year, and you know the corrosion rate, whether the mass loss is significant or whether the damage because the pitting is significant. And here's a chart which I was telling you about, that by just comparing your photograph with these charts which are available, you can find the cross-sectional area of the pit and the depth of the pit. And you have the thickness of your material that you are using, and you know exactly how bad is the damage to your material, whether it needs replacement or not. So all this information is available. And how we do the corrosion analysis, which many of the consulting organizations do, is just a very simple slide here. And what we do here is that if we encounter a case of corrosion failure, then what we should do is to first get all the important information. Some of you are sending me some of the information about the failures you are seeing at your end. So basically, if you really want to have a solution, if you really want to arrive at a solution, you should get everything. What is corrosion? Interaction between a material and environment. So you have to get everything about the material that you are using. You have to get every fine detail of the environment that your material is subjected to. So these are the two prime things that you need to get from your end. So you get the corroded part, take a few pictures, find out what material, what grade material you are using. Stainless steel is not good enough, 304. Then 304 is not good enough. You have to find out whether it's 304 or 304L. So everything is important, every fine detail is important. Then you have to find environment, inside, outside, contamination, no contamination, presence of industry, no presence of industry. So you have to see around it, what you see, what you can practically record. You have to do that, and then you have to see whether your part is stressed or not stressed, because once it is stressed, then you have to see stress corrosion cracking, corrosion fatigue, hydrogen damage, what is the possible situation that you can encounter. So once you get all this thing, then you have to characterize our material. If you recall the World Trade Center, the damage was because of the sulfidation, and they found it out by the microstructural examination. So many times if you have the samples, you have to do the chemical analysis to ensure that the corrosion is not because of a bad material. You have to do the macro examination. Macro examination will tell you whether it's a fatigue failure or not, corrosion fatigue for example. You have to do the micro examination to see, for example, whether it's a sulfidation type of failure. You have to do the mechanical testing also. If the mechanical testing results are bad, that means something is wrong with your material to start with. So once you get all this information, you have to analyze all of them or some of them which are more relevant to your situation. Then you have to come out with some conclusion and recommendation, and then you have to request for the implementation. So this is how the basic failure analysis is done. No matter what consulting organization you go to, they follow these steps. But it means also a lot of work. All right. So essentially what we have seen in the corrosion testing is what is the importance and what is the criteria: reproducible, reliable. You can carry out in the lab, you can carry out in the field, and the results in the field testings are the ones which are realistic and which are used for real application. Accelerated methods because you don't have time every time to wait for years to get the corrosion behavior. So it gives you a faster and quicker picture, which is getting more and more accurate with advancement in the technology. You can do that by fog spray method, high humidity, simulated atmosphere, immersion in liquid. And there are many more tests which are coming in, but these are the ones which are established, which people are using for decades now. So that's why they have come in the textbook, but there are many more which has been researched into. And then you have general ways to assess the corrosion damage by the weight change or by dimensional change. Both of them are very important. Then you also have the corrosion type. If you know that your material is subjected to pitting corrosion only, then you focus only in the tests which are related to the pitting corrosion. Then your job is simple. Then you have to see that how do we select the testing method depending on your material and the working conditions, and how to simply do the corrosion failure analysis. So that is all for this module. Now, if you have any questions so far, it was quite a straightforward lecture on the corrosion testing. If not, and if you people do not wish to take a break, then I have the papers for quiz 1. The response of few people is mixed. Some people have done very well, some people have done all right, and some people have not done well. So before you see your quiz and everything, you just see that what you have done, and apparently it is only 15% of your total grade. You still have quiz 2 to go, and you still have the final exam to go. So if you have not done well, put your heart for quiz 2. If you have done well, don't take it easy, because the quiz 2 is still there and the final exam is there. And I've seen that people who have done bad even in both quiz 1 and quiz 2 can get still the B+ grade, provided they do very well in the final exam. All right? So do you people want to have a break and then see the quiz papers, or you want to see the quiz paper now? Now? Okay. What I will do is that it's not arranged in any specific order. So I will just put it somewhere here and you can come down and see. Or you want me to just take the name? Then you have 120 of you. Which method you want? And after every one of you have taken your this thing, then I have the solution for you, which will go through today, so that you know that if you have not got any marks, if you have done wrong something, then what you should have done. All right, let's start with the name only. Khao Meng Wai. Second one is Bao Cheng Yu. Third one is Abhishek Ray Mohapatra. Abhishek, are you there? Dilip Krishna Nandkumar. T. Chi Yen, Teo Chong Leong, Fang Yang Guilin, Navneet Krishnan Karthikeyan. Oh, okay. Fang Yang Guilin, A01621006U. Matriculation number. Not here? Okay. Karthikeyan. Lok Rai Hua Clarice.
Oh no.
No, it's not you. Ending with 1933 M. Wasim Akram Khan. Wasim. The next person is Julfi Kali bin Samuri. Samuri. Yeah. Zhang Jin. Zheng. Zhang Jin with 427, something like that. And then you have Wang Jianfeng Gabriel. Gabriel. And the next one is Huang Xingsen. Matriculation number 2367A. The last 4 digits. And you have Sophie Clarice Genevieve. You are not the one here. So she is the top scorer here. Can you raise your hand, please? Huang Xingsen with matriculation number of A01523667A. Not here. Then we have Zhu Yan, Zuyan. Then you have Lydia Stalin Raghu. Then you have Liu Jinze, Liujinze. Leong Kok Hao. With matriculation number of A016537Y. Lee Yong Wee. All right, once again, A016537Y. Leong Kok Hao. Not here. Okay, Mr. Lee Yong Wee, A01651112U. Not here. Then we have Sayyid Muhammad Hafiz bin Suram. Yeah. He is one more guy with 90 plus. And we have Lim Jian Y. Matriculation number A01475778M. Then we have Xia Kwang Yong. I do not have the matriculation number here. Okay, you people can see later. Then we have Lee Mengsha, A01486662X. Next person is Ling Hui Ting, A01651001X. Then we have Yasmin Muhammad, Yusri Muhammad Abdul Rahman. Then we have Feng Shi, A0046019L. Then we have Lo Kok Leong, A0042966X. And we have Ang Seong Andy, A014711, I think 7226H. Ang Seong Andy. Next person is Tan Yi Jin Daryl, ending with 960R. Then we have Tan Bing Guang, A01504667E. Then we have Lee Jiu Jun, A01294446Y. Next person is Ji Nyan, A01470002X. Then we have Ma Tao, A007868U. Then we have Hyun Sang Yuk, A015095 or 0454M. Hyun Sang Yuk. Then we have Liu Su, Lyusu, Liu Su, another person with 90 plus here. And we have Fang Yu Cheng, A00458004J. Then we have Ong Om Yong. IC number 59046315B. Then afterward we have Mohsen Saeed Khani Jirai. He is another person in the top 5, 90 plus. Then we have Ong Boon Kian. There are many people in 70s and 80s, but I am only like highlighting the people who are above 90. There are almost 10 of that of you, at least 10. Then we have Zheng Baidong, A01522883. Then we have Nyor Yi Hui, A01522272M. Wang Dai, A01522448H. Not here. Then we have Akash Hathi Ramani. Then we have Gan Jun Long, A01523006R. The next one is Wang Xiu Fai, A01523111Y. Then we have Nicholas Ho. After Nicholas, we have Long Ching Tang, A01651441N. Then we have Ahmad Razali bin Saini. After that, we have Gao Chen, A01523333R. Then we have Go Wai Chiang, A00567771Y. And next to him is Pan Bo, A0165148B. Muhammad Alif bin Razali, Wang Damyun, A01623030B. Aishwarya, Mohammad Raihan bin Amroon, Mohammad Raihan, okay. Sun Jihan A00841100. And next to Sun is Lim Ro Sheng A002668. I think it is H. Then we have Ong Vailon A0146965N. No? Yeah, yes. Then we have Lo Cheng Yang, and he is one more with 90 plus. Ravindra Ram Gopal, another one with 90. Suhail Muhammad Hussain, Ramasamy Vignesh, Liu Wenhao, Kang Yu A0162034U, Zhao Guangkan A0162097B, and he is also 90 plus guy. And we have Li Jianqiang, another 90 plus guy, 90 guy. Huang Yu A0152285A, Lihil Utpala Sabasinghe, Zhang Run Yu A0152251U, then Yang Shang A0161583, Fan Jihong A00738886M, and he's one more guy with 90. Kalai Selvan Vimaraisan, Yi Fang Chen, Wu Yun Shan, Hao Yazi 0152416M, Shai Jinyu A0152256J, Saraf Anmol, Siva Apanna, Li Shu A0146584W, Li Shu. The next one is Lao Sai Nian A01653773B, and next one is Bai He A0162049H, Then we have Miao Chenji A0161589R. And then we have Wu Jixin A0162045N. And he has also 90 plus guy. And we have Zhang Xin A0136439Y. Yao YG A0152249E. Another 90 plus guy. And then we have Wang Haiming A0165110X. And then we have Yang Qing, second highest scorer in this quiz one, Yang Qing, with a score of 96. And then we have Tan Boon Chong. And then we have Chi Ming Feng Kevin, A0138. Then we have Xu Shanshan, A0165097W. Then we have Amitabh Ghosh. After that we have Liu Haiyan, A015235A. Then we have Ko Kai Liang Peter. And after that we have Zhao Mingyu, A01465525E. Then we have Fang Junjai, A01523888X. Then we have Paneer Selvam Venkateshwaran. Chang Huaxiang, A01504730L. Then we have Seet Vailia, A01522444N. And then we have Abdul Nabi Muhammad Kot Al Sani. And after that we have Wang Xiaoping, A01465542H. And after that we have Nalla Sivam Manoj Prabhakaran. And then we have Hua Xinglin, A016241X. And after that we have He Hongying, A015250X. Then we have Guan Baiying, A01651116L. And then we have Li Xuan, A01522667E. Then we have Li Yo Ang, A016246M. Li Yu Meng. And he is another guy with 90 plus. Then we have Cheng Mengjia, A01622029L. And then we have Liao Zhenyu, A01622079B. Where is she? Where is Liao Jin Yu? We want to see you. You are third highest, 95. Show your face to everyone. Then we have Li Yuo, A0162068E. Li Yuo. Then we have Wang Mangchi. Please write your matriculation number in your final exam and quiz 2. And then we have Yu Bing Xiu, A0152103B, B as in boy. And then we have T Jing Chong, A0164848N. Xu Li, A0119042R. Xu Li. Zhao Quan, A0056588M. Next one is Chen Chao, A0152191M. Oh, okay. Chen Chao. Then we have Sun Ren Cheng, A015230881, no, 208M. And then we have Shi Wen, A0070613R. Then we have John Gusti, A0056448X. John. John here? No? Okay. Habimana Jean Willie, A014878. I cannot read that one. And you. And he's another guy with 90. And that's all. So last person is also with 90. So now take a serious look at the question paper that you have. You see where you have lost the mark. And as I say, don't lose your heart, because the people who have done badly in quiz number 1 can still get an A, provided you do well in quiz 2 and also the final exam. And final exam is always easier than what you see in the quiz. So prepare yourself. And I'll give you 5 minutes, and then after that we will discuss the answers of quiz 1. Now also do a double check on the totaling, because at times there can be a mistake in totaling. So if you find any mistake in totaling, just bring it to me. All right? And if you feel that your answer satisfied what I'm going to show you in its own entirety, and you have been given less marks, also you can discuss with me. But always remember the kind of answers I'm showing to you. So I'll just take 5 minutes. You go through your paper, because the people who have collected their papers towards the end, I want to give them some time. And after that, after 5 minutes, like say about 7:15, we will start with the answers of the questions that you have seen. And please do not take these papers back to you. We have to submit that to the graduate office towards the end of the term. So after you have seen them, you please return back to me. So once again, all the papers have to return back to me, and they will be sent back to the graduate office after the end of the term, and they are required for the auditing purpose. So we cannot leave the paper anywhere. So ensure that you return your paper to me after you have seen through it, after we have gone through these solutions. Also note that we have the quiz 2 in the next week. And again, the timing is same, 6:15 to 7:15. So try to do your best. It's a closed book exam. and I do not know whether we get chance to discuss the solution of quiz 2 and when you are able to see, but if you want, what we can do is that after quiz we can discuss the solution for quiz 2 right then and there, but you may not be able to see your scripts. Alternatively, if you want to come on the following Tuesday, then I should be able to grade by that time and we can discuss the solution. So I leave the choice on you, what way you want. You want to come on maybe April 18th, I think April 11th is a Tuesday, so April 18th should be a Tuesday. You want to come on April 18th to discuss the quiz 2, or you want to see the solution after the quiz? Which method you prefer? Any preference? Anyway, you think about it, and once we are done with this one, then you can let me know. All right, so here's the quiz number 1 here. The first question was like that. Picture below shows the corrosion of a fire main line control valve hand. Location was in a jetty near Changi Beach. So the hint here is Changi Beach, and Changi Beach immediately should strike you that we are in a humid environment. In a way, anything open atmospheric condition is the humid environment. So I'm asking you what category of corrosion is displayed. So it has to be the wet corrosion. Remember the dry corrosion, wet corrosion. So it's a wet corrosion. Justification, outside location in Singapore and humidity greater than 80%, coating damage over time because people have to use the valve to open this and close this, and that is answer which will give you full 5 marks on this one. All right. Question number 2. Picture below shows the corrosion of coins. Identify the corrosion category. Coins. They are never in the closed condition. They are not in the air conditioned room. They are not in the glove box. They are in your pocket. They are in the open trays. They are exchanging hands, and the hands can have sweat. So it cannot be the dry condition. It is the wet corrosion. And you can give any justification. As long as you give wet corrosion, I accept most of your justification. All right. Now let's go to question number 3 here. I hope this is clear. Can the metals such as copper and aluminum exhibit catastrophic oxidation? Here I'm only trying to test whether you know what is catastrophic oxidation or not, and support your answer with brief justification. So you know that copper and aluminum are inert material, almost inert material, because aluminum has the best aluminum oxide under the dry condition, and aluminum and the copper is also a very stable copper oxide. They follow either logarithmic or parabolic laws. And catastrophic oxidation is exhibited by the materials that exhibit linear law. That means their oxide layer is not protective. So if you know the fundamental definition of catastrophic oxidation, your answer should be immediate no. So if you have written this, you should have got full marks. It's directly from the lecture notes. All right, now let's go to the question number 4. As I say, in the final exam and in the quiz 2, which is upcoming, no need to write too much, but write sufficient to just answer the question. And for that, you need to read the question carefully and see what is asked. More words, more statements will not fetch you mark. The more you write, the more mistakes you are likely to make. So don't do that. Just answer to the point and leave it there. An iron channel is placed in air-conditioned room and be open atmospheric condition in Singapore. Will it corrode in both conditions? If yes, under which atmospheric condition it will corrode more and why? So now here we are trying to compare the dry oxidation characteristic of iron and the wet corrosion characteristic of iron. We have seen that air-conditioned room is less than 60% humidity, so it's a dry condition. And if you recall your oxidation reaction law, iron at the room temperature acts with logarithmic law. But the question is that it corrodes. So if you say it does not corrode, no, that's wrong. All the metals except for gold in the dry condition corrode. Everything corrodes. So the answer is that it corrodes. In the wet atmospheric condition, when you're outside, 80%, it corrodes. So what is the difference? The difference is three differences. First is the category of corrosion is different, and the iron oxide in the wet condition is not a stable or good oxide, it falls off. You have seen brown rust falling off from the iron-based products. Number one, oxide layer is not productive in the wet condition. Number two, the temperature is high outside. A typical in Singapore is 32 degrees centigrade. Inside is maintained 24 degrees centigrade. 10 degrees centigrade difference. Number three, what you get in the air conditioned room is a filtered air. So the contamination in terms of particulate matter and sulfur containing gases, chlorine containing gases, the concentration is much lower in the air conditioned room than outside. So whenever you have any catastrophe, people say, go to your home, close the windows, and stay inside. Why? Because inside, the atmosphere is more controlled than outside. Now, all these three factors increase the rate of corrosion. So these are the three factors. The people who have written at least 2 plus or 3 factors have got full marks. And if you have written less number of factors, proportionately you have got less marks. So air conditioned room is a dry and open atmosphere is a wet corrosion condition. Oxide scales are not productive, temperature effect and presence of contamination. So three things you can imagine. Now, I was reading some papers and I found some very interesting data, which is of course beyond the scope of this module, but still relevant to explain the effect of temperature, because at times the student says that 10 degrees centigrade may not be sufficient enough. But remember, the reaction law or any reaction is exponential function of temperature. So the data which I am going to show you showed the difference of 10 degrees centigrade. Now you see at 25 degrees centigrade pure magnesium, all the black spots are corrosion. So still part of the surface is white. But if you see 35 degrees centigrade, the whole surface is black. So that is what 10 degrees centigrade difference can do to the corrosion of some material. So do not ignore even the minor factors. This paper I just come across came for the review. So I thought I should share this information with you. Suggest whether the dry corrosion resistance of aluminum will increase or decrease with an increase in the thickness of surface oxide layer. This thing I discussed during the lecture. I said the more you make the layer thicker, the more distance the ions have to travel and more time it will take for the corrosion to take place. So this answer was discussed in the lecture many times. So you can say the distance, so you have to answer in two ways. The time taken for the ions will increase, and number two, you can invoke the Wagner's law, where the rate of corrosion is the inverse function of thickness of oxide. So the people who have given these two reasons, definitely 100%, otherwise you might have got either 7 or 8, the way in which you have phrased your answer, logically or not logically. Number 6, this is also straight from the lecture notes. This was testing your concept of exchange current density derived from the lecture notes again. Now the whole purpose is that this question, if you read it carefully, it says that metal M, so metal M is a prime metal that you need to protect, and you have choices to use either aluminum or iron in the acidic situation when there is no oxygen. So I'm specifying that you want to save metal M. So metal M is the one which is going to corrode, and you want to minimize the corrosion of metal M by combining with aluminum or iron, and the atmosphere is acidic situation and there's no oxygen. So your cathodic reaction is straightforward. Now both iron and aluminum are chosen as potential cathodes. So your metal M is still corroding, but you want to minimize the rate of corrosion. So to attach with these things, acidic situation, and I give you the exchange current density in case of aluminum is 10 to minus 10, and while that of iron is 10 to minus 15. Which metal will you choose to protect metal M? Whether you connect metal M to aluminum or whether you connect metal M to iron. That's the question asked. And then you have to show this diagram to explain your answer. So it's a simple question of effect of exchange current density. So you have to see that exchange current density is higher, corrosion is higher. That is the first rule. It gives you 5 marks. You draw this graph, you get another 10 marks. And you answer it correctly, you again get another 5 marks. So essentially what you see is that the exchange current density of hydrogen evolution in case of iron is less, 10 to minus 15 ampere per centimeter square. If your cathodic reaction is slow, your anodic reaction is automatically slow. So by using iron, you are slowing down your cathodic reaction and you slow down your anodic reaction, and your corrosion of metal M will be less. And that is how you have to answer this question. Some people have messed up with 10 to minus 10 and 10 to minus 15, thinking that 10 to minus 15 is more. And some of the students who have got the concept right, I read their answer, I still gave them the benefit of doubt, but of course they will not get 20 out of 20. They will get 12 out of 20. I know that they have messed up only with the number, but their concept is right. All right? And these questions are very straightforward, straight from the lecture notes. Label anodic and cathodic line in the following diagram. So only thing you have to do is write anodic line with the positive slope, cathodic line with the negative slope. This is very straightforward. And then what happens when you have anode covered with a reasonably protective film? Now the reaction becomes anodically controlled, it becomes steeper. So just make it a bit steeper. Do not change the cathodic line. You are not affecting the cathodic reaction, you are only affecting the anodic reaction. Cathodic reaction will automatically adjust. And this is taken from lecture notes when you have the passivity and anodic inhibition. Question number C, again from the lecture notes. Redraw the graph when electrolyte has a reasonable resistance. So they don't intersect, but it's a IR drop. And then you have schematically show in a potential versus current diagram the corrosion system of zinc immersed in deaerated acid. Write their corresponding anodic and cathodic reactions. So these are the standard anodic reaction, cathodic reaction, and for anodic reaction, a positive slope has to intersect with the negative slope of the cathodic reaction. If you have done simply that, you get full 10 marks. No need to write anything beyond what is asked for. Many of you have got it right. As I say, almost 60 to 70% class is beyond 65 marks. So most of you have done well. And then question number 9, look at the diagram below carefully. All the shiny parts are made of same steel. So initially this was also a shiny part which I explained, but some people left early, so they get some benefit of doubt. So all these parts are made of the same thing. Arrowed area is corroding. So this is an arrow, this area is corroding. Location of this object is in a home in Singapore, so humid condition. Humid condition means wet corrosion. Identify the category of corrosion and the anodic and cathodic area if applicable. The area which is corroding is anodic, and the area which is not corroding is cathodic. So that should be your answer. Now why it is anodic side is, some of you have got it correct actually. that this area may be stressed because the shape it has got actually. It is the one which is operated with key or screws or wrenches or whatever, so it has more stress. So some people say it's more stress, it corrodes. Many of you have got it right that way. And the shiny area is cathodic. The one which is not corroding is cathodic always. They are all interconnected. All right, so this is all you have to write. You don't have to write anything beyond that in your quiz 2 and in the final exam. Most of you have done well, but the people who have not done well, please try your best in quiz 2. You are still not beyond A grade. You can still get it. And there's a lot of fluctuation in the people who have done well in the first quiz and not doing well in the second quiz. So please, for the people who have done well, maintain your consistency. All right, so after this, please return your papers to me and you can leave now. And we'll meet next week with quiz 2, so be prepared.